let's talk about materials who are rate dependent. So far we talk of damage models. Materials in which the stress depend on the strain, but not on the rate of the strains. So if I apply certain strains to a material, or I apply the same strains but in a shorter time, the behavior will be the same. The N stress and the N, whatever the properties are, the N damage is the final damage will be the same. Now we are going to introduce the rate dependency. There are several ways to do that. In fact, we will examine two types of what I call viscose regularizations. In general, in continuum modeling of constitutive equations, we always, in general, introduce the viscoelastic behavior as a modification of the not viscose or the inviscid behavior. And that's what is nice of that. We see that we can do that, and that also allows to keep most of our understanding of the model just introducing some little modifications. In fact, what do we have in a rate-independent model? I recall what we had. We had a revolution equation with initial value, which was, this evolution was ruled by the Karush-Kuntucker condition. We have seen this. Okay? Integrating that, we can compute the internal variable. From that, the damage variable. We have the constitutive equation, and we define, to characterize the model, a certain damage function in the stress space or in the strain space, as we wish. Okay. Now, how do we obtain a model that is dependent on the velocity, but keeps the essentials of the damage model? So we can talk about the damage, we can talk about the loading, unloading, damage. We can keep the same, but now we want just to add a new feature, which is the dependency on the damage. It's very easy, it's almost trivial. Just that. Instead of solving lambda through the Kuntucker conditions, Karush-Kuntucker conditions, we forget this part here, and we define lambda in that way. 1 over eta is now a viscosity, times the Macaulay bracket of the damage function, G. Only that. So now lambda is not computed, I insist, through that, but we have a real evolution equation. In the first and the second lectures, when I introduced the evolution equations, I said the evolution equation is a certain function of the free variables and the instantaneous values of the internal values. Now, it was not that format was not so clear in the cases we saw before, but now it is clear. This depends on epsilon r, and this is a constant. So this is just what is called a viscose regularization of the inviscid model, in which the parameter, the damage multiplier, is no longer computed as a loading, as a Karush-Kuntucker set of conditions, as a regularization, that is what's called Persina's type. Maybe you should keep in mind this name. Persina was a Polish scientist, I met him sometimes. Persina's regularization, who was the first one that introduced that. There are other types of regularization, and in fact, when we deal with plasticity, we see that you will pass from plasticity to viscoplasticity by another type of regularization, another family of regularization. I mean that this is not the only way of doing the regularization. And there are little differences of using one or another type of regularization, but they are always the same. We define lambda as a certain function of the internal variables and the stresses. That function is inversely proportional to one parameter, which is the viscosity. So the point is, how much does this change what we saw so far, the algorithm that we have seen? Look, in fact, there is something that is very curious. When eta tends to 0, we recover the Karush-Tucker condition, which is not trivial, but now we'll prove it. So that's a model that approaches the smaller is the viscosity, the more we approach the implicit case, which is, I mean, it's consistent with the name. Implicit, what does it mean? No viscosity. So it should be, but I mean, I could call it implicit and not fulfill this condition. But now we will prove that that definition makes that model, whatever I obtain from here, and the model we have seen so far, tend to each other, tend to be the same as eta tends to 0. That's a very important result. Okay, let's see. For instance, eta is defined, that's something that again comes from the second law of thermodynamics, positive. The viscosities are always positive, and by definition, the Macaulay bracket of G is always positive by contraction of a Macaulay bracket. It's always equal or greater than 0. Then, of course, lambda, if we define as here lambda equal 1 over eta times G, then it's positive, that is positive, so that's positive, no negative. Okay? So that part, we have already recovered. That part, it's already recovered. Lambda is always positive. Okay, we have to recover all this. Second, let's now look lambda G. Lambda is 1 over eta times G multiplied by G. So G times Macaulay bracket of G is Macaulay bracket of G squared. That's very easy. That's proven here. If Macaulay bracket of X is equal to 0, if we multiply this times X, then it gives X squared here and 0 here. So it's the Macaulay bracket of X squared. So this is a trivial result. This can be written as 1 over eta of Macaulay bracket of square. Then I replace this equation. Macaulay bracket of G is eta lambda. So this is 1 over eta times lambda eta squared. I just simplify by eta, and that gives lambda squared eta. So that is eta r squared. Okay. So whatever it is r squared, what happens when eta tends to 0? Lambda G is equal to 0. In the limit, r dot is something, so r dot square is something. When eta tends to 0, this tends to 0. So then recovers that when eta tends to 0, this equation, sorry, this equation here, that equation here. So we have recovered that, and this. Okay? So let's go to this one. So again, Macaulay bracket of G is lambda eta, which is greater than 0. So as eta tends to 0, this term becomes 0. So the Macaulay bracket of G is equal to 0. What does that mean with G? A function whose Macaulay bracket is 0, that means that G is smaller or equal than 0, which is that one. That one. So we have obtained this, that, and that. Okay? Let's go ahead. Another remark. Imagine that lambda G is equal to 0. Okay? So taking time derivative, lambda dot times G plus lambda G dot is equal to 0. Okay? If G is equal to 0, this term dot, lambda G dot is equal to 0. So if G equal to 0, lambda G dot equal to 0, that is that equation here. That equation here. Okay? So this is something which is a little mathematical proof, very simple, but with very physical implicances. We will see that what means is that eta rules how much the implicit model is far from the viscous model. Or the other way, the larger is eta, the more we get away, the model gets away from the implicit one. But as we decrease the viscosity, we get an implicit model with some consequences. Okay. So, that's important. For instance, look, in the implicit case, we said that no point in the static space can lie outside the elastic domain. Okay? And that came from the fact lambda g equal to 0. Okay? Or g is smaller than 0. But here, this cannot hold anymore. So, for instance, again, the regularization said that the square root of g, the Macaulay bracket of g is lambda eta. And that can be different from 0. So if that is different from 0, that means that g can be greater than 0. That means that unlike what happened in the implicit case, one point can lie inside the elastic domain, can lie on the elastic domain, but it can lie also outside the elastic domain. There is no limitation for the point. Of course, the distance at which a certain point can lie outside the elastic domain depends on eta. As eta tends to 0, that distance gets smaller and smaller so as to remain. So somehow eta, the viscosity, controls how much is the Yell function or the damage surface can be overcome by the stress state. Okay? So yeah. No, it doesn't mean that. The damage surface evolves because there is an evolution equation. R dot, what is it? There is an evolution equation. R dot is that, evolves. But it's like if the point, instead of being on the surface and pushing it, and the surface evolving has to keep this point on it, what happens is the point goes outside and pulls somehow, pulls the elastic domain behind him, being outside. Okay? So there is an evolution of the elastic domain. The evolution can be also positive or negative, can be have loading or loading. The only point that is different is that now the point is no longer constrained to stay on the damaged surface. The remaining, or at the interior of the elastic domain, it can be outside the elastic domain. Okay? So, when the point is inside the elastic domain, that is what F is smaller than 0 or G is smaller than 0, depending if we are in the elastic, in this duality of the strain spaces, stress spaces still holds. So if F is smaller than 0, G is smaller than 0. If the point is inside the elastic domain in the stress space, it's also inside the elastic domain in the strain space. In that case, the evolution equation, what does it say? Look at this. How much is this? This negative. The Macaulay bracket of negative value is 0. So lambda is equal to 0, so R dot is equal to 0. There is no evolution of the elastic state. So while the point is inside, nothing is different. Mm-hmm. The point is now the point can be outside. So as F is equal to 0 and G is greater than 0 and G is greater than 0. In that case, R dot, since this is greater than 0, is different from 0. And then there is an evolution. So as the point gets out of the elastic domain, there is an evolution of R as if the point was pulling some way at a certain distance, the surface, and that distance is function of eta. The smaller is eta, the closer is this point to the Yell surface. Because we know that in the limit, when eta tends to 0, the point cannot get out of the elastic domain. See, that's the physical interpretation of the mathematical regularization. Well, so it's very easy now. What is the constitutive equation for a viscous damage model? That's something that you will experience also in your first assignment. Well, the free energy is the same. There is no difference. We assume that the free energy is the elastic free energy, quadratic form, in terms of the elastic material properties, blah, 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 1 minus d. Dissipation equation is the same because there is no difference. And again, we obtain that the stresses are the derivative of the free energy with respect to the strains, the free energy. So this is exactly the relationship of the stresses and the strain in terms of the damage variable is exactly the same that in the implicit model, no difference. And the remaining term, which is the dissipation, is phi 0 times d dot. Again, phi 0 is a positive definite quadratic form of C, so that is positive, so that means that d dot is greater than 0. So again, the fact that we are in viscous damage doesn't mean that doesn't change the fact that the damage variable always increases. Okay, so far it's the same. What changes is the evolution equations. The evolution equation is what changes. That is the point. So we had changed, I want to emphasize that, the evolution equation that said that R dot is a function determined by the Karius-Tucker conditions that with all implications, we have just changed that R dot is now 1 over eta times G, times the Macaulay bracket of G. That's the only thing we have changed. And this has enormous implications. At least the ones that we want to introduce. So another change, important, is the tangent constitutive operator. You have to look at that because otherwise you will get surprised. Look, I just want to recall what I said to you. The definition of the tangent constitutive model is the derivative, tangent constitutive operator, of the stresses with respect to the strains. In the implicit model, T is just a parameter that controls the evolution of the strains and whatever. And the dependence of the stresses to the time is through the strains. What changes now? That T, due to this evolution equation that we have done, T appears although in the equations, so because it appears in the evolution, in the evolution of the damage variable as a new independent variable. That's a big change. So the stresses depend on the instantaneous value of the strains and also on time. For instance, if I keep the strains constant, in an implicit model, the stresses will be kept constant too. Because if the strains doesn't change, the stresses doesn't change either. But here, if I keep the stresses constant, there is still a possible evolution of the stresses. This is what is called the relaxation of the stresses. So relaxation of the stresses is an observed phenomenon in materials that says that if I impose a long time stresses, I can have something like that, I can have something like that, but then if the evolution of strains a long time are that, and here they are frozen, that is strains a long time. That is stresses a long time. That is time, that is time. I increase the stresses, the strains increase, at a certain point they start damaging, I have some damage, and at a certain point I just freeze the strains. In a damage model, the behavior would be like that. In a visco damage model, the behavior is that there is a relaxation of the stresses that allows that can go to 0. Okay? The stresses, the stress relaxation.
Is the same as softening?
No, it's completely different because softening is associated to increasing of strains. So the apparent, that's very important in material science, the apparent effect is the same. You see that you just start that and you see some stress and then you keep fixed the mouth of that are applying the strains, and then you see that the force sensor that is measuring the stresses decreases, but you haven't changed the strain. Strain softening is when doing that, so increasing the strains, the stresses decrease. But this is not the fact. That's a very completely different nature phenomenon. In that case, you freeze the no strains, you have different overstrains. And then also, there is also the so-called yielding, in which under constant stresses, the material yields. So now, if I design another experiment in which which I impose are the stresses, so I have the stresses increasing up to a certain point, and then they are kept constant, and I measure here the strains, I see that the strains start increasing in that way, but beyond that point, if the material was inviscid, the strains would be frozen. But if not, they continue increasing. Okay, well, there will be an elastic branch here and something like that. Okay, these are two typical phenomena that appear in viscous models, and they don't appear in inviscid models. So this is the transition of that is that the stresses depend on the strains, but also by some additional phenomenon, internal phenomenon, on time. Well, what is the consequence of that in the tangent constitutive operator? Well, again, we compute, if you compute the evolution of stresses, that would be the evolution devoted to the evolution of strains minus d dot times c epsilon, which is sigma. That's the same that we obtain in the inviscid case. Okay? Then, if we just replace here this part, that's 1 minus d times epsilon, this is d dot is d prime of r times r dot, but r dot can be replaced as 1 over eta times g. So finally, the evolution of the stresses have one term that depends on epsilon dot, and one term that doesn't depend on any dot. There's no time dependency here. Okay? That is what makes that when I freeze epsilon, when epsilon dot is 0, there is an evolution of the stresses. This term, dependent on epsilon dot in an inviscid case. If you go back some slides, we see that this term here in the model, when we replace we did operations of replacing r dot, blah, 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 finally, r dot depended on epsilon dot. But here, r dot depended on something that doesn't depend on any time variation. And that's the second part, which is exactly, this is the counterpart that corresponds to the derivative of sigma with respect to t. Okay? So, now we have to be careful with that, because we have a derivative of sigma with respect to epsilon, which is this, and a derivative of sigma with respect to t, which is this. What is the tangent constitutive operator that we will need to export in order to be used in linearization, Newton-like linearization procedures? That one, not that one. So that is the important difference. The tangent constitutive operator in inviscid cases is always the second tangent, the second operator, 1 minus d times c, which is the derivative of the stresses with respect to strains. And that second part, and it's just 1 minus d times c, it's much easier. And in order to use that, in order to the linear, what is called the linearization of the model, we need just this part. We don't need that part, which appears in the evolution of sigma, but it doesn't correspond totally to the evolution of sigma with the strains. There is something else. Understood? So that's what I already commented about the fact that in an inviscid model, when the strains are frozen at a certain point, then the stresses in the inviscid model are frozen too. But the strains, but in the viscous model, due to that fact, this fact is frozen when epsilon dot is equal to 0, then this term also decreases, produces some evolution of the stresses, negative evolution, and that makes an exponential decreasing of the stresses.
Can you give a real life example of this phenomenon?
Many. Take a chewing gum, and then just keep that with the same force. With the same force, you will see that if it's well shoot, then you will see that the stresses you have to do decreases with time. You just pull them to a certain extent, and you will see that the force decreases. Eventually it breaks, so that the stresses is not. You don't change the pull, the strains, the external imposed strains. Many other cases, it's plenty of these cases. I remember the first course that I took for that. The lecturer took one of these balls that are not gum. It's that caoutchouc gum that is used, for instance, for racquetball or whatever. Okay, just cut them into two pieces, and then just force one part to be bent, so just to show the inner part to the outer and so on, and keep them into the table. And you will see that after a while, bloom, jumps. It's buckling due to the evolution. You don't do anything. It just at the stress state, you don't impose any strain. It evolves, and that is due to I mean, concrete. Many know that many materials, construction materials, have important effects due to the viscosity. Many. So that's an important effect, which is called the long-term effects of materials. Okay? Time-dependent effects of materials. Okay? And that's it. That's it. What is remaining then? Well, it remains doing for this model, the visco damage model, the same that we have done for the elastic for the inviscid model, the algorithm. And you will see that in fact the procedure is so clean that you can just code, that's the key point, code the viscous problem as the general case, and then by stating the viscosity equals 0, fully recover the inviscid case. So finally, you can implement just both the viscous and the inviscid model in just 10 lines of coding, including one parameter, which is the viscosity, that we can do 0 to model inviscid cases, or differences to 0 to model non-viscid cases. By the way, in the assignment, I'm advancing what you requested in the assignment. You have to do experiments. For instance, one experiment is what happens when the viscosity is very, very large. Very, very large. It can be proven, you will see, that the material recovers a purely elastic behavior. So materials with large viscosity behave almost elastic. That's something that takes place in geology. In geology, depending on the scale, at the geological scale, all material, the earth is done of viscoelastic materials. Everything flows. Everything flows. At the instantaneous time that we are, and at the short scale, which is ours, I mean, we don't see this flowing. But you know the famous plates that are moving for the initial, Pangea, and then it's moving. That is just a matter of viscous behavior. So in geological issues, viscosity plays a fundamental role. Okay? At the scale of millions of years, if you were able to see that at this scale and make a movie and advance from million to million years, you will see everything moving like a fluid almost. Okay? And by the way, that there is a way to relate, not exactly, viscosity behaviors like with fluids. Okay? But that's another story. So